Chem activity number 23 and the corresponding video, we're going to look at the hydroboration of an alkene. In order to understand how this works, we need to do a little bit of background context. And so I'm providing some definitions of Lewis acid and Lewis base. So in addition to the Bronsted-Lowry model, which was proposed in the 1920s, at about the same time, Gilbert Lewis, as in Lewis structures, proposed a different sort of model, where he looked, instead of whether or not a proton was being donated or accepted, he looked from the perspective of what's going on with the electrons. Is an atom in a molecule electron rich, in which case he referred to it as a Lewis base, or is the atom electron deficient, in which case he called it a Lewis acid. One of the things that you will see is that a Lewis acid can also be considered as an electrophile, and therefore a Lewis base would be considered as a nucleophile. To help you see how this works, I'd like to show you a reaction that you're very familiar with. And so this is HCl reacting with H2O. We'll use the curved arrow notation to emphasize the organic chemistry aspect of this. And of course the products here are the chloride ion and the hydronium ion. Now we know that HCl, of course, in terms of the Bronsted-Lowry model, will be our acid, and in turn, the water will be our base. Fortunately, as it turns out, this is also true for our Lewis model. So the HCl is still a Lewis acid, and the water is a Lewis base. So we know that in terms of the Bronsted-Lowry model, the HCl is a Lewis acid because it's the HCl that donates a proton to water, and we know that water is the base because it accepts a proton. From the Lewis acid perspective, we know that the hydrogen here is electron deficient. This is why the oxygen in water is attracted to it. So a Lewis acid, a molecule with an atom that is electron deficient. In turn, the water is acting as a Lewis base in the sense that that oxygen is electron rich. So that would be delta negative. And of course, it's the lone pair of electrons that will now make a new bond to that hydrogen that comes from the hydrochloric acid. So it's looking at the same reaction but from a different perspective. Perhaps you can see that the model of Lewis acids and Lewis bases is actually really quite important in organic chemistry because it's quite consistent with the whole idea of the curved arrows. Another thing that's actually quite helpful is to look at a molecule and decide whether or not it has a Lewis acidic atom, and also try to decide which atom would be the most Lewis acidic atom, that is the most electron deficient. So of course in hydrochloric acid it is the hydrogen that's the most electron deficient, and therefore it will be that hydrogen that interacts with a Lewis base or a nucleophile. So now let's extend this to some other examples. Now we've seen a number of reactions that have involved the hydronium ion. And so for instance, if I draw here an alkene, and as we know, the first step in an acid catalyzed addition of water involves the picking up of a proton by the pi system in the alkene. Now we know in terms of calculating formal charge that it's actually the oxygen that has the positive charge. So you might have wondered, well, why isn't the alkene attacking the oxygen, which is where the positive charge lies? Well, certainly formal charges are very helpful in accounting for the electron distribution and accounting for all the electrons that are present. And indeed, the hydronium ion overall is missing an electron compared to the number of protons that are present. But we know that there's more to the story. So for instance, we know that oxygen is considerably more electronegative than the hydrogen. So while the oxygen bears the positive formal charge, to some degree that's attenuated by the fact that the oxygen is more electronegative. Electrons are being pulled along the sigma bonds from the hydrogen towards the oxygen. And in fact, it's the hydrogen that is the most Lewis acidic atom. So I'm just going to label that here. And of course I could pick any one of these hydrogens. So again, this is why we expect when an alkene reacts with the hydronium ion, the pi system picks up or makes a new bond with that hydrogen rather than interacting with the oxygen. It's also useful to consider, well, what about the carbocation then? Can we think of a hydrogen that's bonded to a carbocation as actually being the most Lewis acidic atom? But the thing is, carbon is not as electronegative as oxygen. So electron density really isn't being pulled much from the hydrogen. Now we do know that to a certain degree, the positive charge is attenuated in the carbocation by having these alkyl groups here. And so there is stabilization by induction as well as stabilization by hyperconjugation. And therefore, we would say that the carbocation here is the most Lewis acidic atom. And if we had a nucleophile in solution, for instance, a chloride, and if this, for instance, was the intermediate in an electrophilic addition reaction, as we know, the chloride attacks at the carbocation. It doesn't attack at the hydrogen there. So we've seen an example of the hydronium ion, where although it's the oxygen that bears the formal charge, it is our hydrogen that's the most Lewis acidic atom. In the case of the carbocation, it is actually the carbon with its positive charge that's the most Lewis acidic atom. Now, here's another example that's more relevant to what we need to do with the hydroboration. So I ask us to draw the Lewis structure for borane. So let's do this together. So boron is in the middle, and then we've got hydrogens attached here. You may recall that boron is one of those atoms that usually will break the octet rule by having too few electrons. So you can see that this boron does not have an octet, rather it's only surrounded by 6 electrons. Now if we consider, for instance, the electron distribution, this is a unique situation in which the boron is less electronegative than the hydrogen. So in fact, we would say the boron is delta positive and these hydrogens are delta negative. I realize that there's not a very large difference in electronegativity. We're just looking at a difference of 2.0 to 2.1. Apparently this is sufficient to make this boron be the delta positive atom or the most Lewis acidic atom in this molecule. This has interesting consequences. So for instance, if we expose the borane to a nucleophile, such as a pi system and an alkene, that pi system will be attracted to the delta positive boron instead of the hydrogen. So for so many of the mechanisms that we've seen, the pi system has been attracted to a hydrogen, whereas in this case, it's going to be a boron. So case of point, let's compare these two reactions and the formation of a predicted intermediate. So in the first case, and of course this can be the acid catalyzed addition of water, we will form the more stable carbocation, positive charge here, and then just for emphasis, we know the hydrogen would have been added on the least substituted carbon. In the case of borane, where the most Lewis acidic atom is the boron, we will now expect the pi system to attack the boron, and the intermediate that we would expect to see here will be that the boron is out at the outer edge, and we've got a carbocation here. So there are actually some really strong similarities. It's still the most stable tertiary carbocation that forms, but instead of having a hydrogen on the least substituted, it's actually the boron reagent that's on the least substituted. Now, actually, there's a formal charge on this boron in this particular case. Now, before I go on, I just want to emphasize that this is not an accurate intermediate. So we're going to see that we'll be changing our viewpoint in a minute. But I'm drawing this just to emphasize that it's still the idea that you have a more stabilized carbocation on a more substituted carbon. We might expect for the reaction written below that the next step would be something like this, where the pair of electrons connected between the boron and the hydrogen would actually attack at this carbocation, in the sense that, of course, now that whole region has high electron density. Now that's going to be ultimately the outcome, but it doesn't occur exactly like this. Now notice that this is going to give a different sort of outcome, where the hydrogen, in fact, is acting as a nucleophile here, and it will be the hydrogen that ends up on the more substituted carbon. Up until now, the hydrogen has always ended up on the least substituted carbon, and then another nucleophile or a different nucleophile attacks at the carbocation. You may now suspect, therefore, that we're leading to what's called an anti-Markovnikov reaction. It has a regiochemistry that's anti-Markovnikov. Now, one of the reasons why we know that the reaction doesn't occur exactly like this is because notice that in this particular case, the hydrogen with its pair of electrons could actually attack from either side of that trigonal plane or carbocation. And that's not what we see. So in fact, what happens is when the BH3 ultimately is added as BH2 and an H, the H and the BH2 are always added on the same side. Now, this would not be true if in fact there was a full carbocation intermediate, because the hydrogen as a hydride could attack on either side of the carbocation. But rather, the H and the BH2 always end up on the same side. So we call this a syn addition. And that's referring to the stereochemistry. In order to explain what's happening then is we actually believe that there is no full carbocation. Rather, we have the pi system, for instance, attacking at the Lewis acidic boron, but simultaneously the pair of electrons between the boron and the hydrogen are attacking at the more substituted carbon. Therefore, the H and the B will be adding on the same side. But again, it will be that the hydrogen, technically that's our nucleophile, will be attacking the more substituted carbon. So in the end, we'll end up with this product right here. Now, at first, this may not seem very useful, but the thing is, the BH2 can easily be replaced in the following reaction. So the idea is once that BH2 has been formed, then we simply oxidize the BH2 using hydrogen peroxide under basic conditions. So now the outcome is, as we see here, we've got an H and an OH added to the same side. Of course, there will be another product that would form, the stereoisomer, where the methyl group would be coming out at us. The H here would be going away, as would the OH. So both of these products will form, but we will not form a product where the H and the OH are trans to one another. So we say that this reaction is stereoselective and it's a syn addition. We also, of course, have the regiochemistry where this is an anti-Markovnikov. Now, just to emphasize this, if we, for instance, started with an alkene that looked like this, and then the reaction involved acid catalyzed addition of water, so let's say we use HCl cat here, we know that the product in this reaction, the OH, would be added at the more substituted carbon. Now, the stereochemistry is not so important in this particular case because this carbon right here is not chiral. And of course, the hydrogen would be added to the least substituted carbon. So we know what we have just drawn here is an example of a Markovnikov addition, and what we saw with the hydroboration is an anti-Markovnikov. Now be careful, this is not anti-stereochemistry, this is anti-regiochemistry. So perhaps it might be a good idea to say, okay, Markovnikov addition, regiochemistry, anti-Markovnikov addition, regiochemistry. And in terms of stereochemistry, well, I'm going to write none for the reaction at the top there. But of course, what we mean is it's neither anti nor syn, whereas the stereochemistry for the reaction that we've just seen is syn. Now you'll notice that I state here the mechanism of the oxidation of BH2 to OH you're not responsible for, but do note that this oxidation happens without affecting the stereo or the regiochemistry. So we'll do some more practice with this in our live sessions, so as you start to see that this is a very useful tool if we need to have an outcome of an anti-Markovnikov addition rather than a Markovnikov addition.